Hello, welcome back. This is part two of the normal distribution. Please make sure you've seen part one, which introduces the idea. In this video, we're going to look at applying normal distribution. So we ended with this idea that under a standard normal curve, we have these set percentage areas between the, here's the mean, and within one standard deviation of the mean, less or more, we have 68% of the data. Within two standard deviations of the mean, we have 95% and 99%, almost 100% of the data within three standard deviations. Make sure you have that ready as we proceed to the next part. So what we have here is a curve, standard normal curve, a shaded area, and you just have to say, what is the probability of data falling within that shaded zone? Well, in that case, should have been pretty easy. Right from the previous diagram, 68.3%. We are one standard deviation from the mean. And by the way, this is just another way of writing mean, right? You can write it like this, or you can write it like we saw it here with an X bar. Okay, so that's just that zone, that first zone, one standard deviation below and above, 68%, written as 0.683 as well. How about this one here? Well, in this case, you can be thinking of it as, well, we are two standard deviations from the mean, but we know that's 95.5%, but that's only if you're two standard deviations above and below, but there's symmetry here, so I can say 95.5 divided by 2. So it's that whole 95 zone divided in half, and that gives us 47.75% or 0.4775. So that would be the probability of data being within that zone. Next one, how about this one? Well, in this case, we have that first zone within one standard deviation and half of it. So again, 68.3 divided by 2, that gives us 34.15%, which is 0.3415. How about here? In this case, I looked at the 95 zone, which is that full zone up to 2 standard deviations, and I subtracted away the middle zone, the 1 standard deviation zone, and divided that by 2. So it's like saying this whole area minus this area and then divided in half. So that gives us 13.6% or 0.136%. Sorry, 0.136. All right, how about right here? Well, that one's easier than the ones we've just been looking at because it is clearly that 2 standard deviations above and below, so we know that's the 95.5% zone, or 0.955. And last one here. In this case, we have 100% if you took everything minus the 95% zone and divide that in half. Because if you subtracted the 95.5% zone, you'd be left with both tails here, and I'm just having one of them. So divide by 2, and that gives us 2.25%. So very little bit of the data lies in that zone. Okay, so now let's start using it. We have this example of T, which is a variable measuring the waiting time in seconds for customer care for a representative for the TechCo to respond to a customer's first question in an online chat session. So imagine you go to this company's webpage and you need some help with their products. You go to an online chat to get some help from somebody, and T measures how much time it takes them to respond to your message that you've sent in the online chat. It says here that T is distributed normally with a mean of 19 and standard deviation of 3, or variance of 9. Okay, so let's label this first. So we have the mean, 19, and since there's a standard deviation of 3, we can go down 3, up 3, down 3, up 3, down 3, up. Oh, I didn't go to the last one, but anyway, we get the idea. So first one, it says, what's the probability of having a T value less than 17? So what's the chance that you wait less than 17 seconds for a response? So I drew a line here representing where 17 would be, somewhere between 16 and 19. And we know that we're somewhere in the middle here of that first zone, but we want to find the area right here, less than 17. So we want this area. What's the probability of that response being less than 17? So let me show you how to do this on the calculator, because notice that this 17 does not lie on if it was 16, it would have been an easier question to answer, because we would know that's the 68, 95, and 99 zone, right? But when it's somewhere in between zones, we can't get that exact percentage, so we're going to lose our calculator. So here's how we do it. So you're going to do like we did previously with binomial distribution, you can press second and vars, which is distribution. And now we see normal here. Before we went to binomial here, but on the main screen, I'm going to press it again. On the main screen, right away, we see normal. And just like with binomial, when we want to see from one point and everything below it, we're going to use the CDF, not the PDF. We're going to use CDF to do a cumulative, okay, probability. So I'm going to press number 2 for CDF. Now it says lower, upper. What it means by lower and upper, it means what is the lower number and upper number we're going to use. So in this case, the lower number, well, if that curve keeps going, imagine that curve going to infinity. So notice they have negative 1 to the e. This means 1 times 10 to the negative. Sorry, negative 1 times 10 to the I'm wrong there, sorry, like 1 times 10 to the negative 99. It's a huge, small number. I can clear that just to show you, but basically you're trying to say, I want to go as far in this direction as I can. So I'm going to make a giant negative number, negative 1, 0, 0, 0, 0, right? It's huge. Compared to these numbers of 13, that's a huge negative number. It's basically saying go as far down as you can. Next one, upper. Well, the upper number in the zone we're trying to create here is 17. It's the question here says 17. So 17, and then we're going to put in the mu, or that's the mean, right? The mean is 19. And then the standard deviation is 3 here for standard deviation, and then paste is when you're done with that. So, and now enter again, and it gives us this value here, 0.25. It's saying 25% of the data lies in there. That's our answer to that first question. So we have normal CDF, and that answer is 0.252, 25% of data. Okay, next one. So now that you've learned that, how about finding the probability that the t-value, the waiting time, is 21 or less seconds. And just so you know, in normal distribution, it doesn't matter whether you have equal to or not equal to. It all works the same, because that line there and that equal to that line, it has no meaning in terms of the probability. Okay, so hopefully you calculated that the same way, and you got a probability of 0.748, means about 75%. And that should make sense, because 21 would be right here. I would draw a line up here. That's not a very good place for 21. Maybe that's for my next one. But anyway, 21 would be right here. And if anything below that would be a lot of the data, about 75% it tells us. Because we have half the data to here, that's 50%, and then you have even more. Okay, let's try the next one. What if you're looking for the time being greater than 20.3? So now I have that line, there's 20.3, and now I'm looking for shading this part here. So greater than 20.3 is here. So see if you can sort that out running the CDF. How would you do that? So greater than 20.3 ends up being 33% of the data here. And how would we do that? Let me just show you in case you had trouble with that. Second, distribution. Again, we're doing normal CDF for cumulative. And now, in this case, since we're looking for this area here, the lower bar is at the 20.3, the starting point. And the upper, now the upper, we want this, again, to go to infinity forever here. So I'm going to put a huge positive number, 100,000, 1 million, whatever that is. Okay, the mean is still 19, standard deviation is still 3, and we're going to go to paste. Enter, there's our 33% right there, 0.33. Okay, finally, well, we're looking for expected value, and the expected value says we're going to run this a sample of 107 chats. So let's say they looked at 107 chat sessions through this tech support, and we're looking for waiting time of less than 21. So we already know the probability of less than 21. We found it right here. So, and if you remember expected value, you just do the number of trials times the probability. So we found the probability to be 0.748. We're doing 107 trials, multiply those. So of 107 calls, you would expect 80 of them about to be 21 seconds or less waiting time. Okay, great. That's a great introductory problem. Let's go to the next one. Try this one out. So for A, we're looking for a fish that is less than 35 centimeters. First, I set up my distribution here. Okay, so to find the probability of a trout that is less than 35, you just used your calculator again and got this number here. Next question. Okay, this one's a little tougher. So we have a probability of trout, more, what's that, 35? Okay, oh, that was the 35 from the last one. Now we're looking for trout greater than 35. See, more than 35, so we do 1 minus that. Or again, you could have run your CDF to show a lower limit of 35 and then above. But we already knew that number, so I'm subtracting that number. So we're looking for this area. It is 0.744. So now how do you deal with at least 2 trout? Well, now this should sound kind of familiar because this is actually binomial distribution, what we did before. So now we're talking about you're doing a sample and a trout can either be less than 35 or more than 35. There's 2 choices. There's a binomial choice there. And we're finding a probability if you catch 5 fish that at least 2 of them will be more than 35, right? So we're saying 2 out of the 5 exceed that probability. So here's our binomial distribution, 5 trials, 5 fish, and the probability of one being more than 35 is this. So we want probability that we have 2 trout out of the 5 that are, or 2 or more. And if you remember to run that binomial distribution, you can do 1 minus probability that you have 1 or less, because 2 or more means 2, 3, 4, or all 5 fish. So if we're looking at, when we do binomial, remember when you do CDF, you have to look for that number and below. It doesn't work like the normal where you can set a lower limit and upper limit. So we have to do the 1 minus this probability. And we get 0.983. Wow, 98% chance that you'll catch that 2 of your fish will be greater than 35 centimeters. That makes sense because there's a pretty big chance that 1 fish will be greater than 35. Therefore, just to get 2 out of 5 to be that length is very likely. Okay, so that's kind of as tough as these problems get, I have to say, where you combine the normal and the binomial. So take a look at this again closely to make sure you understand exactly how that went. Let's look at this one here. We're still in the trout problem, and now we're looking for probability a trout cut is longer than 42 centimeters, given that it is longer than 40. Okay, so now we see this wording, given that. Remember that. That is now our probability for conditional probability formula. Let's try that out. So here's our mean, there's the data. We're looking for a probability that a trout is greater than 42, given that it is greater than 40. Writing out our, I think I have it here, there it is. Writing out our full conditional probability formula, remember that? A given that B, it's A intersection B over probability B. And that's what we're doing here. Probability of A intersection B, and then divided by probability of this one here. Now the thing about the top here is, what's the probability a trout is greater than 42 and greater than 40? Well, if it's greater than 40 and greater than 42, then it must be greater than 42, because if it has to meet both of those conditions, because that's what intersection means, it has to be both of those. The only way a fish can be both of those is if it's greater than 42. So I'm going to simplify that to this. Trout greater than 42 and trout greater than 40. And now you run both of those as a normal distribution on here. So you're going to run a normal CDF for that and a normal CDF for that, and then you'll divide those to get this answer here. So that's kind of tough to combine our skills, but I hope after seeing this example you can see how that can happen, and you have the tools now to do it. Let's look at the last question, D. Determined events are independent. Well, you know that those two are not independent, because when we just found this conditional probability, it did not match the probability of greater than 42. So if 42 dependent on 40 happening is a different probability, they are not independent. That is the definition of independence, right? They would have to, the probability would not change if there was this kind of relationship. Okay, last problem. This one you're going to use your calculator again. Notice in this one, pause and read it because I don't have much time left here. Okay, now that you've read it, we're looking for a distribution that has a mean of 821, standard deviation of 40, so we can set up like this, up by 40, and it says the top heaviest 8%. So this time it gives us the area, whereas before we were given a number, we had to find the area or probability. Now we're given the area, so we say the top 8%, and we want to find out what is that value A right there. What value in this distribution produces that 8%? So we're going to use something called, this is our setup, we're looking for weights that are greater than some unknown value where it gives us an area of 0.08. On our calculator, here's how we're going to run it. We're going to run what's called an inverse normal probability. So if you look at your calculator again, I'm going to press on, second distribution,